Folks, welcome to the October Community Sync call. My name is Bhavani Sudha Saktishwaran. I'm a PMC member of the Apache Hudi project. Here with me are Martin and Kyle. We also have a recording from Yuwei Xiao, since unfortunately he couldn't join because of internet issues. He sent over a recorded presentation. Let's go over the agenda quickly. We'll have short community updates. Followed by that, we have a presentation from Yuwei Xiao for the consistent hashing bucket index, going over the RFC42. And then we have Martin from Apache Flink PMC, who's also a product manager at Imiroc, and Kyle Willer from head of product at OneHouse, discussing Apache Flink and Hudi, going over introductions and use case. And then we can open up the floor for questions. So here are the community updates for the last 1 month. These are taken from the Pulse Insights. So in the last 1 month, we had 132 pull requests landed, authored by 79 people. And we had a minor release, 0.12.1. We have the 0.12.1 release notes are linked here. Please go check out what happened in this release. We passed 2,400 Slack users and 3,600 GitHub stars. And there is a new RFC since last month on Hudi bundle standards. This goes over like the governance process of how to bundle jars, like the artifacts that are externally facing, and what is the dependency, like how do we standardize on those things. Please check out the RFC and let us know your feedback. Okay, without further delay, let's get into the consistent hashing bucket index. I'm just going to play the video here.
Hello, everyone. So today I will talk about consistent hashing bucket index, the RFC42. This work is about index, and we all know indexing is a fundamental component of Hudi. Now Hudi supports Bloom filter index, bucket index, HBase index, and etc. Consistent hashing bucket index, just like the name suggests, could be viewed as a special type of bucket index. So I will start with some backgrounds to present why we need another bucket index implementation instead of using the current one. Next, I will introduce the algorithm and some implementation details. In the end, the progress of the RFC42 will be shown. So background. This image shows the default file layout of a standard Hudi table. We organize the table by partition first, and then by file groups. To get a good understanding of this layout, let us consider two questions. The first one is, how absurd tag record allocations? The answer is index. Taking Bloom filter index as an example, to locate a record, we must load Bloom filters stored on the footer of file groups to do a coarse-grained filtering. After this filtering, we need to load all the full record key of the remaining file groups to do a fine-grained filtering. The idea of it is simple, but the whole process is non-trivial, especially when you have a pretty high false positive rate of the Bloom filter. The second question, when to initialize a new file group? The answer is small file management. In Hudi, every time the file group reaches a threshold, we will create a new one to carry the new incoming records. The default threshold is 120 megabytes. Let us now look at the current bucket index file layout. I name it a simple bucket index to distinguish from today's topic, consistent hashing bucket index. The table is still partitioned by partition key, but on the second level, the bucket concept is introduced to form a one-one mapping between buckets and the file group. So to get the location of a record, a simple hash function is enough by computing the bucket ID. In our experiments, bucket index could achieve 3 times speed up compared to the Bloom filter index. However, simple bucket index does not have small file management since the total number of buckets is fixed and so does the total number of file groups. This will lead to 2 limitations: data skew and scalability. Data skew means the imbalanced data across buckets. For example, 80% of your data are written to 20% of your buckets. This will hurt your write performance badly because only 20% of your parallelism or your computing resources are in use. The second thing, scalability. It means even though we have balanced the data across buckets, with new data streaming in, the buckets may grow infinitely, causing performance issue in compaction or clustering, or even in query. To tackle those limitations, we need to provide a dynamic bucket number layout, and consistent hashing bucket index is our solution to it. So let's look at the basic algorithm of consistent hashing. The image here is simple bucket index. Records are first shuffled to partitions, and then a hash function is applied. Based on this, we add another layer of range mapping on top of it. Records are still go through hash function first, but this time the hash result is a range instead of the bucket number. The hash result is then used as the input to the range mapping, which gives us the final bucket ID. The range mapping adds a little bit extra work compared to pure hash mapping, but the benefit is that now we have the ability to rearrange the bucket layout. Like for this image, take this image as an example. The range of bucket 2 can be divided into 2 sub-range. Showing the image is the green and the yellow color. The 2 sub-buckets are created based on them. The update of the range mapping and the rehash process of bucket 2 is local to bucket 2 only. That means data stored in bucket 1 and bucket 3 are untouched. Meanwhile, if we manage those bucket size well, like each bucket are limited to 200 megabytes, the whole resizing process can be done in a predictable time. This slide we show a split process. Like for in this example, the merging logic is similar. Like we choose 2 adjacent candidate buckets, update the mapping, and then rewrite buckets to produce a new one. So this is the overall basic logic about consistent hashing bucket index. The idea is simple, but still we have extra things to take care when it comes to implementation. The first thing, the metadata. I show an example here. On the right, it is the data file layout. We have 3-level partition. On the left, it is our multi-version hashing metadata. We maintain metadata for each partition independently, and the naming of the metadata contains a timestamp to support multi-version. The initial metadata will have all 0 timestamp. This could help us to handle risk condition in initialization. Also, we choose to store the metadata as JSON formats. It would be easy to visualize and debug. Next, let us take a look at how dynamic bucket is retrieved through resizing. First, the resizing process is implemented as a special type of clustering strategy, considering the semantic similarity between them. So we will have the plan stage and the execution stage. On the plan stage, we first acquire a table level log to ensure a consistent view of the table. Then we find candidate buckets to do merge or split. Finally, we persist the plan, which will include the updated hashing metadata. Next, the execution stage. There will not be any lock, so concurrent write will not be blocked. We just read the plan and execute the plan faithfully. But one thing needs to be taken care when there are conflicts between writers and the resizing execution. Here we propose a method called do write, where writers will observe the ongoing resizing operation, and it will write the conflict records to both old and the new buckets. Specifically, it will use both old and new hash metadata to write the records. Taking the image here, like as an example, the concurrent writer will write to both file group 1 and file group 1.2 and file group 1.1. The good thing with do write is that on the reader side, we do not have to do any change like Presto or Hive or even Spark. They just read as usual. They don't need to have the knowledge about the hash metadata or the layout. As long as the write finished, the new incoming records are immediately visible to the reader. The bad side is that the write performance may be a little bit lower, as some records have to be written twice. But we believe the negative effects should be manageable because the amount of conflict buckets should be small, and the resizing is also efficient. It should be finished very quick. Finally, about the community progress. On Spark side, the core write path is supported in 0.11 version, and the resizing is also merged into the master branch, so it will release in 0.13 version. On Flink side, the core write logic and resizing scheduling is still under review. Hopefully, it will also be released in 0.13 version. The resizing execution of Flink engine is still under development. So before the execution is available to use consistent hashing in Flink, users may have to start a Spark engine to execute the resizing. I put some configs here. Aside from configs of simple bucket index, users need to add another config called the bucket engine. Then the consistent hashing will come into play. Okay, that's all about my sharing on RFC42. Very sorry I cannot be in the meeting and have to do it in a recorded way. But any question or any advice are welcome. And feel free to reach out to me on Slack or WeChat group. Thank you.
All right. Yeah, like Yuwei mentioned, he's a developer at Alibaba. He's the author of the RFC42. Please feel free to reach out to him in Slack. I can give forward the Slack ID of Yuwei along with the reminders in Slack, so to follow up on questions if you have. Okay, let's move on to the next topic.
Maybe a question or two, Suda. It sounded like it's coming in 0.13. Oh, actually, some of it was available in 0.11.
Yeah, the Flink part is coming in the resizing in the Flink part is coming in 0.13.
Okay, nice.
The Spark is available to use.
Okay, great. Do we know of other people that have tried it or used it? I don't know if any of the other Hudi people here.
No, I don't have that thing.
Cool.
Not here, but we have heard some users in the community, they have switched from Bloom to this bucket index.
Okay.
If your data is if you don't have any data skews, even simple bucket index is good enough for your use case because it saves a lot of time in your index lookup essentially.
Nice. So people are seeing good success from it. So
Yeah.
Okay, it's cool.
All right. Martin, do you want to take over?
Yeah, great. Will you click through for me on the slides?
Of course.
Awesome.